So we talked about structural analytics tasks as broken down by this paper in 2012. What are some examples of traversal tasks? So one is to find the minimum spanning tree of a graph. And so that is the smallest subset of edges that connect the graph by some notion of connectivity. So if we ignore directionality, we can talk about weakly connected graphs. So what is the minimum spanning tree of this graph? So we're looking for the smallest set of edges, a minimum spanning tree of this graph, because there might be many that have the same number of edges in them. A minimum spanning tree of this graph. Well, we can get from A to B, and again, we're going to ignore directionality, so there's actually two edges from A to B. So we take one of those. Then we can get from B to F, and we can get from B to E, and we get to B to D, and then we get from D to C and E to G. And so that's one edge, two edge, three edge, four edge, five edge, six edge. And so the minimum spanning tree, the number of edges in the minimum spanning tree is 6. Another way to get 6 is go from A to B and A to F, and then the same otherwise, B to D, B to E, D to C, and E to G. Okay, so there's two different minimum spanning trees with the same number of edges in them. And there are fast algorithms to compute this that we're not necessarily going to go into. So this is sort of a guided tour of various tasks you might want to compute, but we're not necessarily going to describe the algorithms in every case. All right. So another traversal-oriented task is finding paths and circuits. And so the classic example of this is Euler's bridges of Königsberg problem, where the task is to find a path where we visit every vertex and yet cross every bridge in this graph here in the picture only once. And so the observation that was made here was, well, if you enter by a bridge, you must also leave by a bridge. And you can't leave by the same one you came in on because that's the definition of the problem. So this suggests that there needs to be an even number of bridges to every vertex, right? You have to have one to come in on and one to go out on. And then you can come back to this vertex as many times as you want. And so there's two sort of related results here. If you, going from the bottom one here first, if you actually want to start and end on the same vertex, well, the condition is that every vertex in the graph needs to have an even number of edges so that you can come in by one and you can leave by one. And this allows you to make an entire circuit all the way around the graph. If you don't care where you start and end, you're allowed to start on one and end on another, then it's a little bit softer condition. You can, most of the vertices need to have an even number of edges, but you can have at most two vertices that have an odd degree, the one you start on, the one you end on, because you'll need to leave by one, you only need to come in by one. And I'm assuming undirected edges here. The definitions get slightly more complex if you talk about directed, but not much. Essentially, you need to have a balance. You need to have the same number of in-degree edges and out-degree edges. Okay. And so what's nice about this is this is a great result because it's very easy to check this condition, right? You can just add up the degrees of all the vertices in the graph, and you can tell whether one of these circuits or one of these paths exist. But to sort of demonstrate the subtlety of some of these graph theoretic problems, if you make a very slight change to the problem statement, the answer becomes a lot harder. So can we create a path that visits every vertex only once as opposed to every edge only once? Well, this is a hell of a lot harder. And the reason is that intuitively, if you think about it, every vertex has lots of edges, and so it's involved in lots of different paths, lots of different possible paths through the graph. And you're trying to find one of these such paths that touches every vertex only once. Well, given that this vertex is involved in lots of different paths, you're only allowed to use that vertex one time. And so you can imagine that it's difficult to figure out what is the best way to use this vertex. There's a whole lot of different conditions you have to consider. Okay. A related problem is, assume there's a cost to traversing each edge. Right? There's a distance you have to travel, for example. Can we find a path that visits every vertex only once, but also has the minimum cost out of all these? And so there's no efficient algorithm that can exist for these problems, and so heuristics and approximations are the best we can do. And this extension here is the traveling salesman problem. Okay, so these might be some of the tasks you might want to do. These actually come up, I would argue, less often in a big data context, especially this one, in part because it's such a difficult answer to compute. And also, it's not clear that it's all that useful, say, in a social network context or in a web analytics context. You're not necessarily trying to find paths that touch every single vertex in the entire web. So this tends to be, the only times when you're interested in touching every vertex in a graph, I'll claim, is when the graph is in some sense small. Okay. So this is less of a big data problem, but it's something to be familiar with if you're thinking about graph analytics. All right. All right, so one more traversal task, just to be familiar with, is maximum flow problems. So here the input is a graph with labeled edges indicating the capacity at each edge, and then special vertices, sources, and sinks. And the idea is to find a subgraph that maximizes flow between sources and sinks. And so the observation here is that for each vertex, incoming flow must equal outgoing flow. Okay. And so in this example, if A is a source and F and G are the sinks, then you can think about a subgraph where you just have A directly to F because it's only one hop away. And so the flow between them is 2. But if you look at a path A to B and then B to F, you get the flow of 4 here and the flow from, or the capacity of 4 here and a capacity of 3 here, which means the maximum flow along this is 3, right? There's some unused capacity on this edge, but 3 is still higher than 2, and so we want to include that in the subgraph from A to F. Okay, and then to get over to G, you can do sort of a similar walk and say, well, one path is B to D through a capacity of 5, and D to E through a capacity of 2, and E to G through a capacity of 2, and so the maximum flow here is 2, while A to B, B to D, D to C, and C to G, the maximum capacity is 3. This edge is the weak link. Okay, so it looks like the max flow subgraph is ABF DCG, or rather the edge AB, the edge BD, the edge DC, and the edge CG, and the edge BF.